Hi, welcome to our second program in our look at the complex number system. In this program, we're going to look at a little bit more advanced procedures for dealing with the complex number system. In particular, we're going to look at the multiplication of complex numbers. We're then going to define something called a principal square root of a complex number. We're going to define something called the complex conjugate, and then we're going to look at the division of complex numbers. And so the first thing we want to do on this list is look at the multiplication of complex numbers. Okay, to multiply complex numbers, we're going to look at an example here. So let's multiply 4i times, in parentheses, 2 plus 3i. Now, as you look at this problem, you might say, gosh, you know, this looks similar to some problems that we've done before in algebra, something like 4x times 2 plus 3x. And your assumption here might be, well, could we, or your idea might be that since they look so similar, could we apply the same procedures? And the answer to that is yes. Just like we do with other algebraic multiplications, we'll apply the distributive property of multiplication here. And so the process works very similar, except there's one significant difference, and that is in dealing with the i's, as we'll see in just a minute, that there is a part of it that we have to be careful with. And so what we're going to do is we're going to take the 4i and we're going to distribute it to the 2 to get 4i times 2. We'll take the 4i, distribute to the 3i, and so we'll get 4i times 3i. All right, now we'll just do the multiplications here. So 4i times 2 gives us 8i. 4i times 3i gives us 12i squared. Now notice here, that's, you know, we would get x times x would give us x squared. The same thing here. We get I times I gives us I squared. All right, now some of you might say, well, gosh, all right, I'm done. You know, algebraically, if it was x's instead of i's, we'd be done. But since we're dealing with the complex number system, we're not quite done yet. We now need to simplify I squared to negative 1. All right, remember that was one of our basic definitions back when we looked at the 4 exponential forms of I, that is I to the first power, I to the second, I to the third, and I to the fourth, and that I squared is going to be equal to negative 1. So here what we're going to do is we're going to replace the I square in the expression with a negative 1. So let's go ahead and do that and see what happens. All right, so we got down to this stage right here where we had 8i plus 12i squared, and now we're going to replace I squared with negative 1. So we have 8i times 12 times negative 1. Well, we're almost there. We need to write the answer in standard form. And so what we're going to do is we're going to take the 8i plus 12 times negative 1. And again, we're going to multiply 12 times negative 1 to get negative 12. Okay, so that's a real number, so that goes first. And then our 8i goes second, because recall, our standard form here is going to be a plus bi. And so we're putting this answer into that standard form here. All right, so when we multiply 4i times 2 plus 3i, we end up with negative 12 plus 8i. Okay, so that was a multiplication of, basically from algebra, we had a monomial term times a binomial, and so that was basically the same thing we do in algebra, except we noticed that the I squared now comes into play in the fact that we have to translate the I squared into negative 1. And so there's the big difference between just a regular algebraic multiplication and multiplication with complex numbers. That type of scenario where we have I squares being translated into negative 1 happens fairly frequently. Now let's look at a little more complex number for multiplication here. So moving along, okay, now let's look at another problem, and it's a little more complex problem. And so let's multiply 4 minus 2i, which is in parentheses, times, in parentheses, 2 plus 3i. Now, like you saw in the previous problem, we did similar techniques that we've applied in the past as far as algebraic methods. And so we're going to do the same thing here. We're going to notice that these two expressions that we're multiplying, while they're complex numbers, look very much similar to two binomials from any algebraic expressions that we'd be multiplying, two binomial expressions. And so we're going to apply the similar, or actually the same methods we did when we multiplied two binomials. That is, we're going to use the FOIL method. So let's go ahead and see how that's done. Okay, so as I said, just like we do with other algebraic multiplications, we apply the FOIL method. And so here, I've put the whole FOIL method out here for us. We haven't totally completed the problem, but let me work through the steps here with you. Okay, so the FOIL method says what we're going to do is, again, the F says we're going to multiply the first term in each expression. So we're going to multiply the 4 in the first parentheses times the 2 in the second parentheses. So 4 times 2, that's our F for our FOIL, our firsts. Then we're going to multiply the outers. So we'll multiply the 4 times the 3i. And so that's going to be our outers, so we'll get 4 times 3i. Next, we multiply the inner terms, so the negative 2i times the 2. So that's our I from our FOIL method, the inner. Now remember, notice that the 2i in the first expression here, in the first parentheses, has a negative in front of it. So we need to carry that negative through with it as we multiply. All right, then finally for the FOIL method, we're going to do the last. So we're going to do the 2i times 3i. All right, so, and again, that 2i is negative, so it's negative 2i times 3i. All right, so we've got the products written out here. Now we're going to simplify. And so next in the process is we're going to say, all right, the first term here is 4 times 2. That's going to give us a positive 8. We have 4 times 3i. That's going to give us 12i. We have negative 2i times 2. That's going to give us a negative 4i. And finally, we have negative 2i times 3i. And that's going to give us a negative 6i squared. All right. And again, we've applied the FOIL method. We've now just simplified, right? We've simplified the products. And now the process would be to collect like terms. Okay, so the 8 can just be pulled over because there's no other real number in there right now. And then we have 12i minus 4i. Well, 12 minus 4 gives us 8, so we'll have 8i. And then next, we'll just bring forward the negative 6i squared, because there's no other I squared term in there. All right, we're not quite through yet, okay? Again, algebraically, if this was an algebraic problem, and that was an x instead of an I, basically you could stop right there, and you'd have 8 plus 8i minus 6i squared, and say, all right, that's what we're done. But we're not done here because we have the I squared in there. And so once again, we've got to simplify the I squared to be equal to negative 1. So in doing so, we're going to start off here, and we're going to start off from the last term that we had and continue on. And so we're going to take the 8 plus 8i minus 6i squared, and we'll take a look at that I squared, and we're going to convert that to negative 1, with everything else staying the same, the 8 plus the 8i. Okay, so now we have 8 plus 8i minus 6 times negative 1. Well, negative 6 times negative 1 is going to give us a positive 6, and so therefore we end up with 8 plus 8i plus 6. Well, once again, we're not quite there yet. We see we have now 2 real numbers, 8 and 6, and so we're going to finally write the answer in standard form. And so in doing so, we're going to see from that last step there, we were at this stage right here, we had 8 plus 8i plus 6, and then we're going to add the 6 and the 8 to get 14, and then just bring over the 8i. And once again, our standard form was a plus bi here that we're fitting this into. All right, so what we can conclude here is that when we multiply in parentheses 4 minus 2i times 2 plus 3i, which is in parentheses as well, we're going to end up with 14 plus 8i. Okay, so we're going to, as I said before, the multiplication is very similar to what you did algebraically, and I've stressed that to hopefully make you feel a little more comfortable with dealing with the complex numbers in the multiplication. But once again, the biggest difference is that we have the I squared in there. So what you want to do is, as you're dealing with the I squared, convert those into the negative 1. All right. We're going to now move from multiplication to looking at ways to manipulate complex numbers. And the first thing that we want to do as far as the way to manipulate is complex numbers is to look at the definition of the principal square root. Okay, so the principal square root is this. Given any positive number p, the negative number negative p has a principal square root of the square root of negative p is equal to I times the square root of p. Well, the question you might ask is, so what? Big deal. Okay, and what's the big deal here? Well, the big deal here is that if we're multiplying two radicals, both of which have a negative radicand, that is, the number underneath the radical has a negative in, then what we need to do is convert each of those radicals to the principal square root and then do the multiplication. Okay, so there is a use for this, and so let's take a look at it. And so here's our problem. We're going to multiply the square root of -9 times the square root of -7. And so here goes. First, we're going to use the principal square root and convert from the square root of -p to I times the square root of p. And again, we're going to do this for each radical. So first, we're going to take a look at converting the -9. So underneath the radical. So the square root of -9 is going to be equal to the square root of 9 times the square root of -1. Again, we've seen this previously, that we could separate this out in previous program, that we could separate out the radicals this way. All right, so this leaves us with the square root of -9 equal to the square root of 9 times the square root of -1, and that just comes out to be equal to what? The square root of 9 is 3, and then we convert the -1 into I, so we end up with 3i there. Well, what about the square root of -7? And we're going to do the same thing. We're going to pull out the -1, the square root of -1. Now notice here I put this as the square root of -1 first, and then the square root of 7. So what I wanted to show you here is that you could write it either way, all right? But as we move along, notice the advantage of writing it as the square root of -1 times the square root of 7 is that the I is going to come out in front, so we have I times the square root of 7. Because again, we're not going to rewrite the square root of 7 into decimal. We're going to just keep it the way it is, and because we want to get the exact answer here and keep it as the exact answer. Also, you want to be careful, because what happens is a lot of people say, can I write this as the square root of 7i? Yes, you can, but be very careful that that I doesn't sneak underneath that radical. Notice when I've written this, I'm going to circle the I out there. That I is outside the radical. So you've got to be very careful with that. All right, so let's finish up the problem, the multiplication. So what we did is we wrote the principal square roots for each of these radicals. And so we're going to bring over here the square root of -9 is 3i. The square root of -7 is I times the square root of 7. And now we're going to multiply. All right, so there's the coefficient here is 1, so we're going to multiply 3 times 1 and get 3. We're going to multiply I times I, get I squared. And we're going to just actually, technically we multiply the 3 times the square root of 7. I said there was a 1 there, but we're going to bring through that square root of 7. So what's going to happen here next is we'll have 3i squared times the square root of 7. And once again, that standard procedure we have, we see an I squared, we convert that to what? We convert that to -1, and so we have 3 times -1 gives us -3 square roots of 7. All right, and so that is the correct way of working this problem. All right, the thing that happens is a lot of people want to multiply the -9 times the -7. You can't do that, okay, because again, as you do that, they're both imaginary numbers. And so with imaginary numbers, you can't just multiply the negative and get a positive. And we've got to be careful of that because it's a very rigid procedure to how we got rid of that negative, right? Because we had to go through I, and I squared gave us -1. So the -1 was pulled out of this expression as we did this through the I squared. All right, so be very careful with that as you're working through these problems. Do not multiply and say, oh, I can get rid of negatives by multiplying -9 times -7. That's not the proper procedure. Using the principal square root is the proper procedure to simplify these types of problems. Okay, next what we want to do is we want to take a look at something called the complex conjugate. Okay, and there are two definitions of the complex conjugate. The complex conjugate of the expression a plus bi is going to be the expression a minus bi, so that when we multiply a plus bi times a minus bi, we end up with a squared plus b squared. Now notice what happens there when we multiply. The i's disappear because we'll get an I squared, which will be the square root of -1. And again, we have two expressions here in parentheses. Again, basically they're binomial expressions where one is positive and one is negative. So if we do the FOIL method, the middle terms will disappear there. All right, there's also a second form of this, and that's if we start out with a minus bi, then it has a, and that should be plus. I'm going to make an adjustment here. That should be plus bi as its conjugate. And so the same thing happens. A minus bi, a plus bi, if we multiply them, we'll end up with a squared plus b squared. Okay, so basically what happens is the conjugate has the same two terms in there, but with opposite signs in between them. Okay, so that's basically if you observe as you look at this, what's happening there. All right, so let's see what happens as we work with the complex conjugate. And so what we're going to do here is we're given that the complex conjugate of a plus bi, so I've restated the definition there, is a minus bi, so that a plus bi times a minus bi is equal to a squared plus b squared. We want to show that that 2 minus 3i is a complex conjugate of 2 plus 3i. All right, so how are we going to do this? Well, here we're going to just multiply. Okay, we're going to multiply and see if we end up with a squared plus b squared. All right, so once again, in the multiplication, we're going to apply the FOIL method, right? So again, we're doing our FOIL method. So we're going to multiply 2 times 2, so that's the first. We're going to multiply 2 times negative 3i, so that's our outer. We'll multiply 3i times 2, that's our inner. And we'll multiply 3i times negative 3i, and that's our last. So once again, we've just applied the FOIL method. First, outer, inner, last, just like we did in the previous problem. Okay, as we've done in the previous problem, what we need to do now is simplify. So what we're now, and there's something a little different going to go on here. Notice I have 2 times 2. I'm writing that as 2 squared instead of 4 because I want to see if I can fit this form of a squared plus b squared. I'm going to multiply 2 times negative 3i. I get negative 6i. I'm going to multiply 3i times 2. I get positive 6i. And then I multiply 3i times negative 3i. End up with negative 3i quantity squared. All right. Now what I'm going to do is I'm going to continue to simplify. All right. So what happens? Well, okay, a lot of stuff happened here. Well, the first thing that happened was that this 6i, this minus 6i plus 6i, those cancel each other out, right? Because minus 6 plus 6 gives you 0. All right, so I bring down my 2 squared, and then what I did was I brought down my negative, and I rewrote this. Remember that if we have a power outside of parentheses, we can distribute that power into each of the items inside the parentheses. So I'm going to distribute the 2 to the 3 and have 3 squared, and the I to and the square to the I. Well, once again, we're seeing pop up I squared here, right? So what we're going to do is we're going to take that I squared and convert it into negative 1. Now, I'm resisting the temptation of squaring the 2 and squaring the 3 here. All right, there's a temptation, but again, because we want to come back here and prove a squared plus b squared. Okay, so what ends up happening is I have negative 1, and there's a negative out in front, so negative times a negative gives me a positive. So I end up with 2 squared plus 3 squared. And so I can see, I can put a big check mark here and say, yes, hey, we've reached what we want. That 2 minus 3i is the complex conjugate of 2 plus 3i. And part of this is I wanted to show you how the multiplication works and how we can make that quick step that if I was multiplying, if I just give you the problem to say to multiply 2 minus 3i times 2 plus 3i, that you could have just up here, let's put the plus there, that you could have just up here written this as 2 squared plus 3 squared automatically by the definition of using the definition of the complex conjugate. Okay, and then simplify that down. Okay, so the reason why we show that is because we're going to use the complex conjugate as we do divisions, because divisions of complex numbers are kind of an interesting situation, because we know that if we have a complex number, we have a radical in the denominator, and so we effectively have to rationalize the denominators. And so there's a way we can do that using the complex conjugate, which makes our life a whole lot easier. So let's take a look at the division of complex numbers. Okay, so what we want to do is we want to divide 5 plus I, and we're going to divide that by 3 minus 2I. Okay, so here what we're going to do is I'm going to once again show you the process of going through this. And so the first thing that we want to do is to divide. We actually multiply the numerator and denominator by the complex conjugate of the denominator, which in this case is going to be 3 plus 2I. Again, we look at the denominator here and just take the opposite sign, that's the opposite of the sign that's in between the two terms, and that really develops our conjugate here of 3 plus 2I. All right, that said, well, how do we go about doing this? All right, so I've put up a couple steps here at a time so we can talk about this. So notice what I've done. I've started out with the basic problem here that we started out with, and we're going to multiply, as I say, multiply the numerator and denominator by the complex conjugate. So that's what's happening here. This is the complex conjugate. Let me circle this with blue here. The complex conjugate, we're multiplying both the numerator and denominator. And you might say, okay, well, why can we do that? Well, remember, 3 plus 2I divided by 3 plus 2I, that's just another form of 1. Again, any quantity over itself is equal to 1. So we're safe in doing this. All right, and so what we're going to do here is we're going to apply, again, the rule that says a plus bi times a minus bi is equal to a squared plus b squared. And where I'm going to apply that to this is that's going to happen here in the denominator. And so I'm going to bring this down, and notice in the denominator that I just rewrote this as 3 squared plus 2 squared. So I applied the complex conjugate directly there, and you know, that worked out really nicely. I didn't have to go through the multiplication. So if you remember that formula, you don't have to actually do the FOIL method on the denominator. And so I took that shortcut here to emphasize to you to use the shortcut and make your life easier. However, up in the numerator, we can't take that shortcut. So again, we're applying the FOIL method by taking 5 times 3 to get our 15 there. That's our first. We're going to take the 5 times 2I. That's our outer to give us 10I. We'll have I times 3 as our inner, as 3I. Then I times 2I to give us 2I squared. Okay, so we've done the multiplication of the numerator. All right, now we've got to do our simplifications. All right, so in the denominator, what happens is I just square the 3, square the 2, so I get 9 plus 4. In the numerator, well, what did I do there? In the numerator, I brought down the 15, and then I said 10I plus 3I gives us 13I. And then once again, notice that we have the I squared going on up in the numerator, so I squared becomes negative 1 here, so I have 2 times negative 1. All right, so as we examine this problem, again, we're just in the numerator collecting like terms and then making that transformation of I squared into negative 1. Now, we're not quite through yet, right? We're not quite through here. We've got several steps to do yet. So let's continue on and take a look at those steps. So again, we got down to this stage where we have 15 plus 13I plus 2 times negative 1 over 9 plus 4. All right, so next what we're going to do is, again, we're going to simplify to collect like terms. All right, so we bring down the 15 in the numerator. We have the 2 times negative 1 gives us negative 2 here. Okay, so that term right there. And again, bring down the 13I. In the denominator, we take 9 plus 4, it gives us 13. All right, well, we're almost there. Next, we're going to take 15 minus 2 gives us 13. Again, we have in the numerator. So we have 13 plus 13I all over 13. We're saying here that we've got i's in there, so we've got to remember that we have a complex number here. So we need to put this in standard form. All right, so what I'm going to do is I'm going to separate this out. All right, and this is a step that sometimes throws a lot of students. And so basically, just take the first term in your numerator and put it over your denominator, as we did here, 13 over 13. Take the second term in your numerator, the 13I, and again, put that over your denominator, so to get 13 I over 13. Well, 13 over 13 gives us 1. And what happens? 13I over 13 just leaves us with I. And so we've completed the division here. So therefore, 5 plus I divided by 3 minus 2I is equal to 1 plus I. Notice we still have a complex number here, that I is equal to the square root of negative 1. Doing it this way is a whole lot easier than keeping a square root of negative 1 in the denominator. Okay, I know sometimes a professor or somebody will challenge you, and instead of writing the number in complex form, we'll put the square roots in there with a negative underneath the radical as a radicand. So when that happens, just convert it back to the complex number form, the standard form, using I as being equal to the square root of negative 1, and then proceed as we just did here with using the complex conjugate and multiplying the numerator and denominator of the fraction by the complex conjugate. And again, you're applying familiar methods, the FOIL method that you've done probably for a couple of years now in different algebraic situations. And so that's one of the things I want to stress to you, is just use those familiar concepts here with the addition of the concepts that are associated with the complex numbers and the imaginary unit, the square root of negative 1 equaling I. Okay, so what we have seen here is that we want to note also that we always put our answers in standard form here as well. Okay, I want to just a little note on that slide about the standard form and just stress that to you. I know I've said this over and over again, that standard form is A plus BI, but again, we want to make sure that you understand that and always put your answers in standard form when you're dealing with complex numbers. Okay, well, we've come to the end of our discussion of complex numbers in this program, and here we've looked at the multiplication of complex numbers, and we saw that it's very similar to the multiplication of algebraic expressions, with the exception that we had to be sensitive to what happens in the algebraic expression when we get an I squared in there in our multiplication of complex numbers. That was what was different than multiplication of just regular algebraic expressions. We defined the principal square root, and that allowed us to multiply two radicals, both of which had something like we saw a negative square root of negative 9 times the square root of negative 7, where we had negatives underneath both radicals, and that is the radicands were negative. We've looked at the definition of the complex conjugate, saying that if we had A plus BI, its conjugate is going to be A minus BI. And finally, we looked at the division of complex numbers, and in those divisions, we used the complex conjugate to make our life easier, and we had a formula that allowed us to multiply and end up with A squared plus B squared in our multiplication of the denominators when we were working with division, and we saw that actually division turned out to be multiplication with the complex conjugate. Okay, and so this ends our program on the discussion of complex numbers. Thank you.